Okay, so let me begin. First exercise, fairly straightforward one. Solving a quadratic equation. Solve the equation z squared plus 4z plus 5 equals 0. Well, first of all, a clue in this question is if we work out the discriminant, which is equal to b squared minus 4ac. If we work out b squared minus 4ac, in this case that is 4 squared minus 4 times 1 times 5, which is 16 minus 20, which equals minus 4, which is less than 0, and that means that the equation has no real roots. Hence this being in a complex numbers section. We can use the quadratic formula as you normally would to solve any quadratic equation. We have z equals minus b plus or minus the square root of discriminant, all divided by 2a, and we just worked out the discriminant, so that saves us a little bit of calculation effort. So b in this case is 4, so we have minus 4 plus or minus square root of minus 4 over 2. And what we can do here to make sure we get the imaginary number I in our solution is to rewrite the third minus root minus 4 as root minus 1 times root 4 over 2, and then this leads us to get minus 4 plus or minus I, and then root 4 is 2 divided by 2, and this gives us the two complex solutions to the quadratic equation. We get minus 2 plus or minus I. So that's how to solve a quadratic equation with real coefficients where the discriminant is negative. And that works for any quadratic equation of that form. One important observation as well is that when you solve for z, if 2 plus I is a solution, then, or minus 2 plus I rather, then minus 2 plus I conjugates, represented by the bar, which is equal to minus 2 minus I, is also a solution. So, in general, whenever you have a polynomial equation with one of the solutions being a complex number, the complex conjugates will also be a solution to that equation. Okay. Question 2. Given that we're given several complex numbers now, given that v equals 2 plus I, w equals 3 minus 4i, and z equals minus root 2 minus I, find the following: a, v plus w, b, w minus z, c, vz, and d, w over v. These are quite straightforward if you just know the rules of addition, multiplication, subtraction, and division for complex numbers. If we want to evaluate v plus w, we just take the real parts and imaginary parts and group them together. So just writing out the whole thing in full first. Okay, so we have v plus w, and we just group together real and imaginary parts. So 2 plus 3 plus I times 1 minus 4, which gives us the answer 5 minus 3i. Okay. Part B is very similar. we're just doing subtracting this time, and we do something pretty much identical with 3 minus 4i minus, and then minus root 2 minus I. What we can immediately do is change the minus into a plus and change the sign of everything inside this second bracket here, giving us 3 minus 4i plus root 2 plus I. And then all we have to do now is just group together real and imaginary parts again. 3 plus root 2 plus I times minus 4 plus 1, and the answer we end up with is 3 plus root 2 minus 3i. Again, that was straightforward. Now to find Vz, let me just draw a line to distinguish between the different parts. To find Vz, what we have to do now is just expand the brackets as we usually would. V is 2 plus I, and Z is minus root 2 minus I. We expand the brackets like we would with any factorized quadratic. We get minus 2 root 2 minus I root 2 minus 2i minus I squared. And it's important to know that I squared is equal to minus 1. So we have to use that. And so if we group together the real and imaginary parts, we get minus 2 root 2 plus 1, and then plus I, and then minus root 2 minus 2. It looks a bit more complicated because we have an irrational number in there, which doesn't help to simplify things, but that's the simplest form it can be in. Okay, then now w over v, dividing w by v. We just write out the quotient, 3 divided by 3 minus 4i divided by 2 plus I, and then what we have to do is multiply the numerator and the denominator of this fraction by the conjugate of this, of 2 plus I. So the conjugate of 2 plus I is 2 minus I, running out as a fraction, 2 plus I, 2 minus I, and ideally these cancel out to 1, because that means that the overall value is unchanged and we're just getting it in a simpler form. This is basically like rationalizing the denominator when dealing with surds. So this is kind of like realizing the denominator. We just expand the top and bottom as usual. We get 6 minus 3i minus 8i plus 4i squared. And then on the denominator, it's a difference of 2 squares that would be formed, so we only have to worry about the 2 times 2, which is 4, not 2 there, and then I times a minus I, which is minus I squared. If we expand it, or simplify it rather, on the numerator and denominator, and use the fact that I squared is minus 1, we can get something simpler and more useful. So 6 minus 11i minus 4, all divided by 4 plus 1, and then we have something considerably nicer here. We have 2 minus 11i over 5, or alternately 2/5 minus 11/5 I, and that is the solution to that. All in all, that wasn't too bad either, so